Oh man, I tell you, I just recorded 20 minutes of video without any audio on it. Yeesh. Okay, audio's working this time. So, now we're gonna do a fun thing. Before we go on, lesson 1 and 2 had their own sectional assessment. Lesson 3 and 4 together had their own sectional assessment. That was pretty big. Lesson 5 is going to have its own sectional assessment, all in one. In part because it's a lot of theory. I didn't want to lump it in. I don't want to lump it in with lesson 2 and 3 because those are very graphy and very calculation heavy. The theory here is pretty important, and it's got some skills that I want to make sure that you have. And lots of the subsequent chapters that we're working on are based on the theories that we're going to be talking about today. So yeah, essentially it's a lot of theory. There's a couple practical things in it that rely pretty heavily on function notation, but once you get the hang of it, you should have no problem. I expect you to be able to do this whole assessment in like a week. So let's start. We're going to be talking about inverse functions. In this particular lesson, we're focused on arrow diagrams. So you remember when I was writing functions in terms of arrow diagrams? You're only going to see arrow diagrams this particular lesson. Okay. So at the end of it, you're going to be able to recognize when an arrow diagram of a function is one-to-one and invertible. You'll know what those mean. You'll be able to define an inverse function with an arrow diagram. That means if I give you an arrow diagram of a function, you'll be able to write out your inverse function. You'll be able to define the domain and range of the inverse, so you'll know what those mean in that context. And you'll be able to use the arrow diagrams to test whether or not a function is the inverse of another one. So there's a lot of writing, but it's pretty fun. Okay, so to start us off, here are two. Here are two functions. Recall that how do you use a function? You put in a number 10203, and then you follow the arrow down 2506886. Okay. So these arrow functions represent two things. I went into class one day and I did a survey. And I wrote down all the students' names, and then I wrote down their student numbers, and then I made an arrow diagram telling me the relationship between the student number and their phone number. And I measured everybody's heights. And then I made another function relating their student number to their height number. Okay. So here we've got two functions, and it's pretty fun. Now, all right, before we go on, yeah. This one, you input the student number and get out the phone number. This one, you input the student number and you get out the height number. Now, these two functions are different in a really interesting way. I mean, in one part, yeah, okay, their outputs are different. Don't worry about that. They're different in a whole new, technically important way. And one way I can kind of hint at that relationship is to have us focus at first on their domain and range. What's the domain of f? It's all of the inputs to the function. So 10203, 41072, 91407, 82378. Okay, so why didn't I include this one on the list? It's because it has no arrow attached to it. The function doesn't tell me the output for their input. Maybe that person doesn't have a cell phone. Maybe they weren't in class that day. My function doesn't know about that person. So if I enter that in, my function will say, I don't know who that person is. What's the range? It's all of the destination arrows as a collection. 2502237, 2506886, 2503245, and 1029913. All right, so why isn't this one in it? Well, it doesn't have any arrows going to it. So yeah, I mean, I don't know. It doesn't have any arrows going to it. What are you gonna do? Okay. Well, what about the domain and range of our g function? Domain, again, 10203, 41072, 91407, 82378. I'm not including the bottom one because it has no arrow attached to it. Range 125,200,186. Fun. Well, what about 211? That doesn't have any arrows going to it, so I don't include it in the list. Okay, so the big hint about what's up to come is, at least the start of the hint, is to note something here. These both have 4 inputs in their domain, right? But this one has 4 outputs in its range, and this one only has 3. How come? Well, for one thing, you can't have more outputs in your range than there are in your domain. You can't have more because functions aren't allowed to have more than one output. So the maximum number of outputs is the same as the number of inputs. That's the maximum number of outputs. This one doesn't have the maximum number of outputs because 2 of the functions, 2 of the inputs go to the same output. All right, that's a big clue. So this is actually a huge deal because it means that I am allowed to use this function to build a new function, whereas this function, I can't use it to build a new function. What am I talking about? How do you build a new function out of this? It's not so hard. I'm going to get rid of all this so you don't have to see it. It's not so hard. All you do is you take your arrow lines and you switch them the opposite way. The blue lines relate the same columns of information. They just go from right to left instead of from left to right. And these are called inverse functions. I've inverted the lines. I've turned them around. Inverted. I've inverted the function. We denote inverse functions with a little label. Little -1. You think of the, why f at all? Well, the deal here is that f is the name of the original function. G is the name of the original function, okay? This -1 part says I belong to f. I am its relative. I belong to G. I am its relative, okay? So the idea here is this inverse function, the original function took in a student number and spit out a phone number, and your new inverse function takes in a phone number and spits out a student number. And this one takes in a height number and spits out a student number. Okay? That's the basic idea about inverse functions. It's essentially a reverse lookup phone book, or, you know, the issues thereon. Now, before I go on, I mentioned that you were allowed to use this one to build an inverse function, but this one doesn't work. I wonder if you can think of why. I mean, I switched the arrows around just fine. And the idea here is you can use these arrows, right? You can go f -1 of 1029913, and it'll say, okay, start here and follow this arrow up. The answer is 41072. That's whose cell phone this number corresponds to, right? Why can't I do it with one and not the other? Well, the answer is that it works for the most part. Except for, what if I plug in 186, that height? You start here and you go and you, oh, that, wait, which answer is it? Is it 10203 or is it 82378? Which is the right answer? It has to be unambiguous. You remember that from us talking about functions. You're not allowed to have two outputs for any one input. So because this input has two outputs, this is not, oh, no, you're not that way. Hold on, let me make this neater. Boop, 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 boop. By reversing the lines, I've made a new arrow diagram that's not a function. So the issue of, can you flip the arrow diagrams? You can always flip the arrow diagrams. It's just sometimes you don't get a function. And that's neat because what we've just seen is there are some functions that have inverses and some functions that do not have an inverse. It does not have an inverse. Great. Okay. How can you tell if a function has an inverse or not? What was it about this function that let it have an inverse, and what was it about this function that didn't let it have an inverse? Is there a way for us to look at the expression just off the top of our heads and say, yes, this definitely has an inverse? Well, the answer is here. I've just recopied the diagrams. They're kind of gross. So somebody gives us two diagrams like this. Here are two different functions. Which one of these has an inverse? Does one of them have an inverse and the other not? Well, the short answer is this one doesn't have an inverse. Why? I mean, we just argued that it didn't. But it doesn't have an inverse because there are two inputs that lead to the same output. Now, there's nothing wrong with that in a function. It happens a lot. There's all sorts of functions where two inputs give you the same output. It's okay to have the same output for two different inputs. It's just that limits whether or not a function can have an inverse. So this is a property we call one-to-one. One, two, one. Okay? For each input, there is a unique output. Two inputs don't share an output. That's what one-to-one means, right? And so you see that in this case, it's one-to-one. And in this case, two inputs share an output. There's one term in here where more than one arrow end at that place. Whether or not something's one-to-one has nothing to do with it, whether it's a function. It's just an additional property. It's like yellow-haired dogs. Something can be a dog and not have yellow hair. We're just talking about, of these dogs, some of them are yellow-haired. If a function is one-to-one, then it must have an inverse. In other words, it's possible for it to have an inverse. You're allowed to write out the inverse. And so we call it invertible. So figuring out whether or not a function is invertible comes down to recognizing whether it's one-to-one. So in this next exercise, which function is invertible? Find it and write out its inverse. Okay, so we've got three functions here. Which of these functions is invertible? Figure out which one's invertible, and then when you know which one's invertible, write out its inverse function. We'll get to that in a second. But first off, which one's invertible? That comes down to which one of these is one-to-one. Now, there's multiple ways of checking which one's one-to-one. Essentially, one way of doing it is start with each of these and follow the water slide and make sure you get to somewhere new. That one doesn't go anywhere. This one goes here. This one goes here. So each of these have their own unique destination. So this one is 1, 2, 1. What about this one? Nope. Fine. Oh no. These two have come to the same destination. So it's not 1 to 1. Not 1 to 1. It's not 1 to 1, so it's not invertible. The easiest way actually to tell if a function's invertible is just to scan the output column and look to see if there are any arrows that end up at the same place. So this expression here is not invertible. And if you're paying attention, look at this term. Two arrows start there. It's also not a function. Got to be careful with your arrow diagrams. All right. So we figured out which one of these is invertible. It's the first one. The other two aren't. I'm going to erase them so we have a little bit of room to work. Delete. Okay. Let's write out the inverse of the function. Now before I go on, you can write out its inverse in the following way. It's not good, but you can do it. We'll talk about why it's not good in a second. But let's just do it. Switch the arrows around. And then you call those red arrows, let's see, the input here is y, and the output is x. Okay, and you can say, there, I've written the inverse function. Go away. The thing about that is that it's gross for two reasons. The first one is we're used to using x as the independent variable and y as the dependent. So we're used to using x as the label for the input, and y as the label for the output. And if you do it this way, y in this notation is the name of the input, and x is the name of the output, which there's nothing wrong with it. It's just a little bit confusing. The second reason this is super gross is that we're used to reading arrow diagrams left to right. So you have your independent column, your inputs on your left, and your outputs on your right. Your names in the phone book is on the left, the phone number is on the right. And writing it this way switches that around, and so it's super gross. So for that reason, although this will work in a pinch, we don't write the inverse like that. Instead, we start a new diagram. Where the input is on the left and its label is x, and the output is y. Now, hold on. Before I go on, if the labels here are puppies and toys, say, then the labels here would be toys and puppies. Because we're still looking up this column and getting to this column. It's just abstractly in terms of algebra, when we use x's and y's, we usually use x to represent the independent and y to represent the dependent. And you're going to see a lot of it, so you better get used to it. Okay, so what do we write in the x column? The hint here is that it's not this. That's not x anymore. X is just a name for the thing that I'm going to input into this function. In this case, the thing you're going to input into the function are these values. That's the domain. Okay? So, 10, 20, 30, 40, 50, 1. The outputs of this function are these. And now I can draw the arrow diagrams. Start from 10, go backwards down this to 2. 10 to 2. Start from 20, go up this rope to 1. 20 to 1. Start at 30, go down this rope to 4. Start at 40, go down this rope to 5. And 50 had no input. Okay? So this is my inverse function. I want you to make a note of something here. When we switch them around, what we're doing here is essentially our f and our f minus 1, both of the function and the inverse function, are essentially just lines. They're lines between two columns. Right? Deciding whether we're talking about f and we're going this way, or we're talking about f minus 1 and we're going this way, is essentially me deciding on what the domain and what the range are. In other words, going from f to f minus 1, I'm switching around the domain with the range to get a new function where the domain is now the range and the range is now the domain. I'm switching this column over here and this column over here. The lines themselves are going to be exactly the same. Oh gosh, what just happened? Oh geez, it's still streaming, but what's the thing? Still offline. Can I be offline? One, two, three. Oh man. 1, 2, 3, 4. Is this working? Stupid technical difficulties. All right. And okay. Sorry. Yeah, weird technical difficulties. I think it'll be fine. Okay, so right before it cut out, I was saying that anytime we define an inverse function, we're essentially just switching the order of the x column and the y column. So we have to be careful when we label them, but essentially we're just switching them back one for each other. So the relationship between f of x and y and this is we're essentially switching inputs and outputs. Okay. In other words, if you just think of them as lines, two columns connected with a bunch of, lines, not arrows but lines, these deciding whether we're talking about this or this is essentially us saying, oh, I am going to the left, I am going to the right. The lines are the same, it's just that interpreting them as arrows are going to be different. Okay? So whenever we're defining an inverse function, we're essentially just switching the x columns and the y columns. We'll try some examples and hopefully it'll be simpler. So the idea here, the overall idea here is if a function is one-to-one, it means that it's invertible. Its inverse exists, and then we can go about defining what its inverse is. Okay, so let's try another example. Here you go. Try this one. I've made two columns. You might as well pause the video and try it yourselves. Try writing out the inverse function here. Okay. All right. So what I'm going to do is I'm going to look up each of these terms in this column and then follow it back. So this 1 over here goes to 3. So I'm going to connect 1 and 3. 2. This 2 connects to the 1. 2. 3 connects with 4. So it goes from 3 to 4. 4 over here connects with 2. So this one goes like that. 5 goes to 5. 6 doesn't go anywhere, and 7 goes to 6. Okay? So it's helpful to be able to essentially switch back and forth between these. Now, I mentioned essentially we're just switching the sides of the column we're looking at the thing, and that's definitely what's going on. But I mentioned domain and range earlier. Let's talk about how this affects the domain and range, because the domains and ranges are going to be two similar sets of numbers here. But for our original function, the domain is 1, 2, 3, 4, 5, 6, while its range, all of the numbers that are attached at the end of an arrow, 1, 2, 3, 4, 5, 7, whereas the range and domain of the inverse function are literally going to be switched. So 1, 2, 3, 4, 5, 7. Are plugged into arrows, and here are all the arrows that are led to. 1, 2, 3, 4, 5, 6. Okay? So it's helpful to think about these things when you're writing out your arrow diagrams. Essentially, you just draw it out. So, one question you might ask is there any way to test an inverse? What makes an inverse function an inverse? The question itself is especially kind of obvious in how confusing it is when we write it out in this way, you know, where x is the name of the input and y is the name of the output. Because if I'm not specifying what type of data this reverse lookup thing is, it's especially really difficult to get a sense of things. So is there any way to test? Test? Does it have a character? What's the thing? So the answer is yes, there is a test. I'm going to teach it to you. But to do it, I'm going to imagine a certain scenario where we're making functions out of different types of data. At the heart of it, inverse functions, you got to be able to do it with this, where they're all just numbers, and so it's slightly confusing. But we're going to go back to talking about it in terms of information. So imagine I've got a room full of dogs. Each dog has a dog tag. I'm going to give each tag a number. But, you know, each number corresponds to one of the dogs. Number 2 is Spot, because you got a big spot. Number 4 is Red, because it's a red dog. All right? I also have a big pile of toys. Okay? Each toy is labeled with a number. Number 11 is the baseball. Number 7 is the bone. Okay? And the thing is, each dog has a favorite toy. And I can draw the relationship between the dogs and the toys like this. Oh, I forgot to get rid of these green arrows. Oh, jeez. Boop, 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 boop. Okay. So in my room full of dogs, this is a function relating the dog to their favorite toy. That's what this arrow diagram. F is for favorite toy. Okay. You notice that F is 1 to 1. Unlike the real world, each dog only has one favorite toy, and none of the dogs share the same favorite toy. So they're not fighting with each other. So that means that I can write an inverse function. I'll do that with green. This inverse function tells me which dog corresponds to which toy. So if I say, hey, whose favorite toy is the toy number 9, you can look up and you say, oh, it's dog number 2. You see? So these green lines represent the inverse function, which is fine. Okay. So, how can you tell if a function is an inverse? What I'm about to tell you is going to be super obvious on this particular diagram, but it's pretty important to understand. The idea here is, if I take a dog name and look it up to see which toy is its favorite, and then take that information and look up to see which dog that corresponds to, I always get my original dog. Let's show you for an example. Which toy is dog number 2's favorite? Dog number 2 likes toy number 9. And then you say, okay, I'm going to use my inverse function to look up to see which dog corresponds to toy number 9. Start here, and you get back to 2. Okay? If you look something up in the table and then you use your reverse lookup on that information, you should get back to where you started. That's the idea. And on this diagram, the reason for that is super obvious. It's because it's the same line going back and forth. So me looking something up, f of 5 means that I'm going this way, and then when I plug that into the inverse function, you follow the same line back to where it started. So this number and this number are the same. Okay? So on our arrow diagram. The reason for this is super simple, but this is essentially the principle. For any input I look up, if I then plug that input into the inverse function, you get back the same original information. And the opposite is true. If I start by looking up a toy, that'll give me some dog's name, and then if I look up the dog's favorite toy, I should get back the same toy. Same. This property is the defining property of an inverse function. If you look up a certain value at 8, that corresponds to dog number 6, and you plug dog number 6 into your function, and go back up the line, you get back to 8. Okay? So the deal is we can use this property of inverse functions, this relationship between the inverse functions and the original function, to essentially figure out what the whether a given thing is an inverse. Now, before we go any further, I want to take a pause and talk about composite functions here. Because over here, we're clearly talking about composite functions. Okay? You take one function, you evaluate it, you plug it into another function. We're talking about composite functions. I want to talk about a way to illustrate composite functions when it comes to writing composite functions, arrow diagrams. So review composite functions and arrow diagrams. Let's make it bigger. Move it farther up. Move it up the page. Oh geez, come on. Okay. So here are two functions. They're not inverse of each other. They just they're related to each other. Same dog toy store. This one relates the dogs to their favorite toys, like in the last one. This one relates the toys to prices for the toys. Okay. By combining the two, I should be able to make a new table, essentially a new arrow diagram that goes from the dogs to their favorite toys. To the price it would cost to buy their favorite toys without thinking too hard about stopping in between. Okay? So the ordinary way to do this would be to say, okay, so f of 2, that's toy number 7, and now let's look up toy number 7. How much does toy number 7 cost? It costs $8. Okay? That's the ordinary way to do it. I want a slightly more efficient way to do it. So what I'm going to do here is I'm going to write essentially 3 columns. Dog, toys, price. 1, 2, 3, 4, 5, 8. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. Okay? Now, the way I'm going to represent this composite function is, first you evaluate f of x, f of dog, I guess, and then you evaluate your g function, taking you from the toy to the price of the toy. So, dog number 1 likes toy number 3, and that corresponds to price number 1. Dog number 2 likes toy number 7, which isn't on this list for some reason. Dog number 2 likes toy number 7, and toy number 7 goes to 8. Dog number 3 likes toy number 2, and toy number 2 goes to 4. And then dog number 5 likes dog number 4 likes toy number 5, and toy number 5 costs This isn't as easy as just drawing it out in one go, but this intermediate step really illustrates the nature of this composite instruction. And you don't need to write all of the intermediate, you don't need to write all these other arrows, the ones that are missing, 6 to 5. Who cares about that? I'm interested in dogs to prices, so all those other arrows that start here and end here, they just mess things up, so don't worry about those. Okay, so does that make sense? So I can use this diagram to illustrate my composite function relationships as a function. So I can call this overall thing f g of f of dog is equal to price. Okay? I think we did that before. Anyway, it's pretty fun. So we're going to use essentially the same way of composing composite functions to talk about testing to see if a pair of function are inverses. So behold, here are three functions. This first one over here, this one here, you start with a student and then you get a dog number. Fine. These other three, you start with a dog number and you get a student number, which is fine. They're three different functions. All of them are functions. I've checked. They all satisfy that property. In fact, they're all, well, no, this one's not. I mean, this one isn't one-to-one, so that's weird. But, you know, they're all candidates. Here's the question. Which of these are inverses of my original function? How do I figure it out? Well, I mean, the simplest way is to go alright, so f of 1 is equal to 5, and then try g of 5, that's equal to 1, h of 5, that's equal to 1, and k of 5 is equal to 2, and that's not right, so that's not the inverse. So you can do it that way. The issue with that, though, is that it takes forever, and it's pretty gross. So instead I'm going to teach you another trick that involves the composite functions we were just talking about. I want you to copy out this expression. We're going to be moving down the page, making new tables like this, but I'm going to be referring to this particular diagram, so it's helpful if you have each of these functions defined in front of you. It's going to come up later. I don't want to keep scrolling up and down the page. Okay, have you copied it down? So, the trick here is that we're going to make tables of G, F, student. That goes from student mean student, and F, G, dog. The idea being that if this expression really is the inverse of this, you'll always get back to where you started. Okay? So, how do we do this? I'm going to scroll down. I'm going to refer to it originally. So, the deal here is, like I said, we're going to test these, both of them, each way. Okay? So, you start dog. Wait, which one am I starting with? I'm starting with this one I just wrote up top here. You're going to make composite functions of these because you're testing to see if you get back to the original place. So this one starts with a student, dog, student. One, two, three, four, 5. 2, 5, 7, 8, 9. 1, 2, 3, 4, 5. So what we're looking for here is you write out the function f and the function g. So f starts with student 1, goes to student 5, and g takes you back to 1. You look up on your original table. I guess I can keep doing this. So 2 starts at 2 and goes to 2, dog number 2, and dog number 2 goes back to 1. Boop. Now start at 3, go to 8. 3 goes to 8, and then 8 goes back to 3. And it might help if you make little check marks as you go. 4 goes to 7, and 7 goes back to 4, check mark. 5 goes to 9, and 9 goes to 5, check mark. All of these have gone back to the original place. You don't just want to test one of them, you want to test it going the other way too. F of G dog equals dog. Check that because you're right. So dog column, student column, dog column. 2, 5, 7, 8, 9. 1, 2, 3, 4, 5. 2, 5, 7, 8, 9. All right, let's start looking those up. Dog number 2 goes to student number 1, and student number 2 goes to dog number 2. Check mark. Okay. Dog number 5 goes to student number 1. Student number 1 goes to dog number 5. Check mark. Student number 7 goes to dog number 4. 4 goes back to 7. Check mark. 8 to 3. 3 to 8. Check mark. 5 to 5. 5 to 9. Check mark. Okay. So going backwards and forwards, regardless of the order, the input always comes back 5 in this way gets you 5 out. You always get back to where you start. And that means that your g of x function is the inverse of f of x. Or alternatively, if you want to, f of x is the inverse of g of x. There's no, there's no first and second here. It's just, that means that they are a pair, okay? And we represent this pair with the -1 notation, but essentially they're a pair. So the long and the short of it is we build the composite function going both ways, and if you always get back to where you start, it means that they're inverses. And this is useful because we can use it to test to see if we have an inverse on our hands, or alternatively we can use it to test to see if one isn't an inverse. Now at this point in the game you might be like, hey, why don't we just make the inverse ourselves and then compare it? I'm like, yeah, you can do that too, I guess. It's not as fun. Also, there's some bigger issues that we're trying to get to, but don't worry about it. That was a good thought. I'm proud of you. Let's try with a different one. Let's try comparing this one and this one. Okay. So h of f student gets you back a student. And if you take h of a dog, that function gives you a student, and you plug that into your f function, you should get back a dog. Let's see if you get the same. Are these two inverses? All right, so 1, 2, 3, 4, 5. 1, 2, 5, 7, 8, 9. 1, 2, 3, 4, 5. All right, so you know how I told you to write those things down earlier? Yeah, so that you could look up them now when you're working. All right, so 1 goes to 5, that's cool, and 5 goes to 1. So this is the f function, and this is the h function. And 2 goes to 2, and 2 goes to 2. All right, so that got you back where you started. That takes you back where you started. 3 goes to 8. 8 goes to 3. Check mark. 4 goes to 7, and 7 goes to 4. Check mark. 5 goes to 9, and 9 goes to 5. Check mark. Okay. So does that mean they're inverses? I don't know. It's definitely possible. We haven't seen anything indicating that they're not inverses. Let's write out the next one. So this one, dog, and then the H function, and then the student, and then the F function, and you get back a dog. 1, 2, 5, 7, 8, 9. 1, 2, 3, 4, 5. 1, 2, 5, 7, 8, 9. All right. So, let's see. You look up dog number 9. That gives you student number 5. Student number 5 gives you back dog number 9. You look at dog number 8. That gives you student number 3. And you look up student number 3, and that gives you dog number 8. Check mark, check mark. You look up dog number 7, and that takes you student number 4. And student number 4 takes you back to dog number 7. Check mark. Student number 5. Dog number 5 takes you student number 1. Student number 1 takes you down to 5. Check mark. Student number 2 goes to there, and dog number 2, check mark. Oh, wow, it's looking pretty good. Dog number 1 goes to student number 1. And student number 1 goes to 5. What just happened? H of 1 is equal to 1. Put that in our F function, and we get back 5. This and this aren't the same. Which just kind of emphasizes that you can test it one way, and you can say, oh yeah, look, they're totally inverses. But if you test it the other way, no, not an inverse. Okay? You gotta be careful. Okay. So, what's the issue here? Why'd this happen? Well, if you think about it like this, inverse functions always just invert their domains and ranges, right? I mean, we just switch their domains and ranges. In this case, the domain is 1, 2, 3, 4, 5. But in this case, the range is 1, 2, 3, 4, 5. So that's fine. In this case, the range is 2, 5, 7, 8, 9. 2, 5, 7, 8, 9. There's one element of this range that isn't in the domain here. So that's the issue. Their domains and ranges don't match. And that's why it's not an inverse. Neat, huh? Yeah, you got to pay attention to these things. Okay, so let's do the last one with the K and in the original student. The last column. K, F, students should get me back students. Dog, students. All right, 1, 2, 3, 4, 5, 2, 5, 7, 8, 9, 1, 2, 3, 4, 5. All right, let's test it. So 1 goes to 5, and 5 goes to 2. 2 goes to 2, and 2 goes... All right, so this definitely is not inverses. Okay, so let's concentrate on the skills. We've gone through all the material. I want you to know what I need you to be able to do from this. Here's the set of skills. Number 1, is an arrow diagram function one-to-one or invertible? I need you to be able to tell me if it's invertible. 2, if f is invertible, write out new column, define f to the minus 1 with a new arrow diagram. That's something I might ask you. I might ask you to tell me about the domain and range of f and f minus 1. So I might ask you for the domains and ranges. Essentially, one is switched from the other. And the last thing I might ask you to do is, if I give you functions, give you two functions, test to see if they're inverses. Okay? So four things you need to be able to do. There's a broader set of explanations and stuff that you need to understand, but it all just comes down to, can you do these four things? So don't get overwhelmed with the task before you. I know it's fairly theoretical, but just focus on these four things. Is it invertible? How do you tell? If it is invertible, draw a new diagram for the inverse. Tell me about the domains of each of these. And then, if I give you two functions, do this composite thing to test to see if they're inverses. All right? Okay, thank you very much. See you later.